This begins our coverage of the two synchronous serial interfaces that are discussed in Chapter 10. These two interfaces are the SPI interface, serial peripheral interface, and I2C, or integrated circuit bus. Both are commonly used in industry. The SPI port requires a minimum of 3 wires, even though almost all the time you require a 4th wire, and is technically duplex. This means that communication occurs in both directions at the same time, even though in practice most transfers are actually only half duplex. That is, you typically ignore data coming in the other direction. Its top speed in the PIC24 microcontroller is 10 megahertz, and it's the fastest serial protocol available. This is best for high-speed serial transfer. It's also very simple from a software usage viewpoint. The I2C port, on the other hand, requires only 2 wires regardless of the number of peripherals. It's only half duplex, and its top speed is 1 megahertz, so considerably slower than this protocol. This protocol, the I2C protocol, is best if you're trying to reduce external pin usage. The SPI port consists of a minimum of 3 wires: serial data out, serial data in, and the serial clock. In addition, you typically need a 4th wire to serve as a device select for a peripheral that you're trying to talk to. In this case, this device select is low true, which means you would assert it low true in order for this device to be enabled. If there's only one device on the SPI port, you can simply ground this input and just have it, the PIC24 would only be talking to one device, and you would not require this extra pin here. However, if you have 2 peripherals on the bus, then you need to have a separate device select for each peripheral, which means you have to use a separate parallel I/O line to talk to each device. Each new device would then require using another parallel I/O pin, unless you wanted to put some extra logic out here to decode these parallel I/O lines. Notice that when we connect multiple devices, that the clock line goes to all devices, so does the serial data in, and so does the serial data out. The line that goes to each individual device is going to be this device select line. Note that the serial data in is connected to the serial data out of these 2 devices. During a transfer, if I'm transferring data from this device right here, then this device select line needs to be low during the transfer, and this is going to enable this device to listen to the bus and respond to any clock pulses that are coming along this clock line. If a device select is disabled, in this case if it's high, then this device will ignore all activity on this SPI port. This shows a byte transmission on a SPI port. Clock pulses are provided by the PIC24. The PIC24 is always the master in this transaction. That means it initiates all transactions. The peripherals are always slaves. That means they only respond to when the master provides clock pulses. In this particular case here, the data is going to be stable and valid on the rising edge of the clock, and is going to be changing on the falling edge of the clock. Notice that data is sent most significant bit to least significant bit. This is reversed from the asynchronous serial protocol that we had previously, that was sent least significant bit to most significant bit. The reason that this SPI protocol is called full duplex is because whenever this is data that's being provided by the PIC24. Anytime the PIC24 provides data, the peripheral always provides data back. So every transfer involves data going in this direction to peripheral and data coming back, even if the data coming back is going to be ignored by the PIC24, and that's often the case. So this shows output data going. Notice that on this edge right here, the output data is changing, but the input data is stable. So here the input data is going to be clocked in by the PIC24 on the falling edge. So the output peripheral would clock in data on this edge, while the PIC24 would be clocking in data on this edge right here. So this is going towards the PIC24, and this is going, this data right here is going towards the peripheral. There are 2 control bits that control how data is clocked out of the SPI port. These 2 control bits are actually standard in the SPI protocol, and there's 4 combinations of them. The clock polarity bit determines the idle state of the clock, either low or high. A value of 0 means that the idle state is low. A value of 1 means the idle state is high. The clock edge determines when output data is valid. A value of 0, as in this case, means that output data is going to be valid on the first falling edge. So here data is valid on the first falling edge. A clock edge of 1 means that data is going to be valid on the first rising edge. There's also a bit SMP, short for sample, that determines when the PIC24 samples input data. When this bit is 0, it's going to sample input data during the middle of the clock period. When this bit is a 1, it's going to sample input data at the end of the clock period. The values for these bits, CKP, CKE, and SMP, depend totally upon what particular peripheral you're trying to talk to, and you have to read that peripheral's data sheet in order to know what values that you should use for these bits. Using the SPI port via our C library function is very easy. Besides configuring the SPI port, which we'll show in another example, there's only one library function that you need, and that's this one right here, IO master SPI. What it's going to do is going to send this value out the SPI port, and it's going to return the value received from this function. This is declared as a 16-bit variable because a SPI port can actually be configured to either do 8-bit or 16-bit transfers, so that's why we're passing in a 16-bit value. Typically we're going to use 8-bit transfers in our example. This is called IO Master SPI 1 because some PIC24 devices have more than one SPI port. So this is going to be the function for the first SPI port in the device. This function calls an error check function here, which is going to check to see if the SPI port overflowed. If your PIC24 device is the master, which we're always going to do in our examples in this course, then this error will never occur because we're never going to have overflow because we're always going to read the byte that's returned. The first thing that we're going to do is we're going to clear the SPI interrupt flag. This is going to be set to a 1 when a complete value has been received. We're then going to write this value to the SPI buffer, and then we're going to wait for this interrupt flag to be set. When it's set to a 1, it means that the SPI transfer has finished, and a new value, the value that got clocked in during the SPI transfer, is now sitting in this special function register, SPI1 buff, and we're going to return this. You have to always read this buffer after doing a SPI transfer, or else you could cause SPI overflow. We want to emphasize two things about this particular function. One, this value right here, whether or not it sends 8-bit or 16 bits, depends on how the SPI port was configured. If it was configured for 8-bit transfer, then it's going to clock out 8 bits and clock in 8 bits. If it was configured for a 16-bit transfer, then it's going to clock out 16 bits and return 16 bits. The other thing about this function is that it will always send this value out the SPI port. It will always return what is clocked in, even if that is simply dummy data or even garbage data. For example, many SPI devices don't even have an SDO line because they're input-only devices. In that case, the serial data in line of the PIC24 would be unconnected. Now, it doesn't mean that data is not clocked into here. It's still going to clock some data in here, but it's simply clocking in garbage data, which your program would ignore because you know that no valid data would be being returned by this device. This slide shows a PIC24 communicating with another PIC24 via the SPI port. This was done as an example. This PIC24 right here is operating in master mode. This PIC24 is operating in slave mode, which is advanced mode that we're not going to cover in this course. It's simply used here as an example. In this particular application, what would happen is the PIC24 master would send a string to the slave PIC24. The PIC24 would then reverse the string, and then the master would then read that reverse string from the slave. So let's start here with the master sending the string to the slave. So here's the SD out, the data out of the master. So it's gonna start sending SPI data. Here's the SPI clock. It's going to send the string M that consists of 2 characters, M followed by an S followed by a null byte terminating that string. Now in this case, the slave does not have any valid data to send back, so all it's sending back is zeros, which is actually going to be ignored by our master program. Once the slave has reversed the string, the master is going to want to read that reverse string from the slave. So how does it do that? Well, in the SPI protocol, in order to read data from a slave device, the master actually has to write data to it. So it knows that it sent a 3-byte string, these 2 letters plus the null byte forming the string. So it's going to send 3 null bytes to get that 3-byte string back from the slave. So the slave's going to clock back out the S, the M, and the null byte terminating the string. So let's say that again. In order to read data from a slave device, the master, which initiates all transfers, has to write data in order to get that data back. The master is providing the clock, which is actually being used to clock this data out. In order to provide the clock, it has to generate this transfer by writing data. Let's examine the details of connecting a PIC24 to a Dallas Semiconductor 1722 integrated circuit thermometer. This particular IC has a SPI port. The pins are serial data in, the clock line, serial data out. We'll connect that to the equivalent pins that we're going to use from the SPI port of the PIC24. So serial data out in the PIC24 is connected to serial in of the DS1722. The clock line of the PIC24 is connected to the clock line of the 1722. And the serial data out is connected to the serial data in of the PIC24. Now, on this particular PIC24 device, these I/O pins from the SPI module must be brought to reconfigurable pins, and we chose these arbitrarily. This DS1722 also has a high true chip enable, so we decided to use pin RB3 for this chip enable. That was again an arbitrary choice. We'll note that this chip enable is high true. The DS1722 is used to measure ambient temperature. There's a configuration byte that we're going to need to send it to tell it what mode to operate in. This bit right here, the least significant bit of the configuration bit SD, determines whether or not the device does continuous conversion, that is, continually samples the temperature and has a byte ready for us to read, or it can complete the current conversion and then enter a low power mode. These 3 bits right here determine how many bits are used for the temperature precision and its format. The more bits that you use for the conversion, the more resolution that you have in terms of how precise the temperature is, but it also takes longer to convert. Finally, this bit right here is used to, if SD bit is a 1, then this bit, when you set it to 1, will start the conversion, and then it's going to be cleared when the conversion is over. So you could actually read a configuration register to see what the value of this bit is to determine if the conversion has finished. So this shows how that we're going to write that configuration byte to the thermometer. We're going to bring our chip enable line high, and we're simply going to send it 2 bytes. The first byte is going to be the address of the configuration register inside the device. So we send an 80, and then we're going to send whatever byte is going to be our configuration byte. So this is a 2-byte transfer. This shows how to read a temperature from the DS1722. Recall that we have to write data in order to read data over the SPI port. So it turns out that it takes 3 bytes. The temperature is always going to be 2 bytes, and it needs another. The initial byte here is going to be the address byte that says we want to read the temperature register. So we send it a byte value of 01. Then we send it 2 dummy bytes. It doesn't matter what these byte values are. And what's going to happen is when we send these 2 bytes, what we're going to get back is we're going to get back the least significant byte of temperature followed by the most significant byte of the temperature. These 2 bytes that return for the temperature form what's called an 8.4 format 2's complement fixed point number. Chapter 7 explains in more detail what this means. In order to convert this to a Celsius floating point number, what we do is we take those 2 bytes, form a single 16-bit value, divide by 256 using a floating point divide, and what we'll get back is the temperature as a floating point number. This shows the configuration functions for our SPI example. Here we're going to configure RB3 as our chip enable for the device, so we configure it as a digital output. If it's asserted as a 1, we'll call that slave enable. If it's asserted to be a 0, we'll call that slave disable. This is the configuration of the SPI module itself. It has a configuration register called SPI1 CON1. These values here, we're going to configure it for the following. 1, we're going to take the instruction cycle clock and divide it by 4 to get a SPI clock of 10 megahertz. This divide by 4 actually involves two separate prescalars. This is the primary, this is secondary prescaler, this is the primary prescaler. We choose this one to be a 1 to 1, and we choose this one to be a 4 to 1. The total will be 1 times 4, so the end result is that our clock is going to be 40 megahertz divided by 4. That will be the SPI clock. We're going to choose clock P bit, the clock polarity, to be active high, and we're going to choose the CKE bit to be a 0. And looking at the data sheet for this DS1722 chip, it was found that these two bits was how that the SPI protocol needed to be configured. We need to configure this SPI module for 8-bit mode, and we also need to configure it for master mode. The rest of this is to map the SDO, the clock line, and the SDI line to remappable pins, which we do here. We then configure our slave enable, which is going to set RB3 to an output. We set that line to a output of a 0 because we do not want our temperature chip to be enabled initially. And then what we do is we enable the SPI module by setting this special purpose enable bit, SPI enable tool 1, that will turn on the SPI module. So this shows two utility functions that we're going to use to communicate the DS1722. The first one writes the configuration byte to 1722 to accept the configuration byte as a parameter. And what this is going to do is going to implement this transaction right here, where we need to assert the chip enable line, send it the address byte of 80, and then send it the configuration byte, and then disable the chip enable line. So we'll do a slave enable first. That brings the chip enable line high. Send it at 80. Notice that we're ignoring the return value that's coming back from IO Master SPI. We don't care what gets clocked into the SPI port. It's not important. We'll then send the configuration byte, and then we'll bring that chip select line back low via our macro slave disable. This function is going to read the 2-byte temperature value from the DS1722. So we're going to implement this transaction right here. We'll write an address of 01. We'll write 2 dummy bytes, and we'll read the least significant byte first and the most significant byte as returned by the writes of these 2 dummy bytes. So let's do that. We're going to raise our chip select high. We're going to send the 01. At this point, we're going to send a dummy byte and get back our least significant byte. We're going to send another dummy byte, and we're going to get back our most significant byte. We're then going to lower our chip select line. Now we have to combine these 2 separate values into one 16-bit value. So the way we'll do that is we'll do a bitwise OR of the low byte with the high byte shifted to the left by 8 positions. That will combine these 2 bytes into one single 16-bit value, and we're going to return that as this function return value. So this is our main function that exercises this protocol. We're first going to do call config basic, as we always do. We'll call config SPI 1 port, so now the SPI port is configured and enabled. We're going to write our configuration byte value of E8 to the DS1722. What this does, this configuration byte, it configures it for continuous conversion 12-bit mode. And now at this point, we're simply going to continuously read values, temperature values from the DS1722. This particular mode, 12-bit, takes 1.2 seconds per conversion. So the first thing that we're going to do is we'll delay for 1.5 seconds. At this point, we know that a temperature is ready. And then we're going to read the temperature. We're going to call our read temperature function to get the 16-bit temperature back from the DS1722. We're going to copy that into a floating point variable that we've declared, and we're going to divide by 256. At this point, this variable now has a temperature in Celsius. We're also going to convert that Celsius temperature to a Fahrenheit temperature here, and then we're going to print all that out using a printf statement. This particular thing is going to, this guy right here is going to print out the raw 16-bit value, and then it's going to print out the Celsius and Fahrenheit temperatures. This shows some sample output of the program running. This right here is the hex value that's being printed out by our print statement. This is the raw 16-bit value. This guy right here is a Celsius temperature. This is right here is the Fahrenheit temperature. These lines are being printed about every 1.5 seconds. At this point, I put my finger on the device to raise the temperature, and you can see the device raised from about 81 Fahrenheit to about 85 Fahrenheit. I then remove my finger from the 1722, and the temperature slowly started dropping.